This is the solution video for question 14 from section B of the 4th sample test for CSAT. In this question, you're in a queue and you are offered free admission if you are the first person in the queue who shares a birthday with someone earlier in the queue. Given this information, you're told that you can sneak into any queue position undetected. And then we're asked which position in the queue do we choose to give us the highest probability of free admission. In this question, we need to make assumptions because there's no way we can accurately model what the real world will be like if this scenario occurred. So, what assumptions could we make? Well, firstly, we're going to assume there's no leap years because there being one day, which is a quarter of the likelihood of any other birthday, massively complicates the equation. And when it's 1 day in 366 with only a quarter probability, it makes very little difference to the actual answer. So we'll just presume there is no leap years. And we're also going to presume any birthday is equally likely because in reality, more people are born in the autumn than the winter, etc., which would change our calculation. But for simplicity, we're going to assume that any birthday is equally likely. So first things first in this question, let's try and introduce some suitable notation. So let's say Pn is the probability of free admission if we are in position N. And we need to find a formula for Pn and then try and maximise that. And if we can maximise that, we find the position we should be in. So Pn plus 1 we're going to work out because that's slightly easier because it means we've got n people in front of us in the queue. So Pn plus 1. So we get this. Where does this come from? Well, we know every combination of the n people in front of us with their birthdays is equally likely because the probability of any given birthday we're assuming is equally likely. So this bottom number is the total number of combinations of birthdays we could have in front of us. So for each place of the n, we have 365 different choices, so 365 to the n. And this is the total number of suitable combinations, i.e. the number of combinations of birthdays we could have in front of us, which means that we would be the free admission. And because every combination is equally likely, this will be the probability we need. So where does this numerator come from? Well, let's suppose we need someone with our birthday in the queue. We need exactly one person with our birthday in the queue. So let's put them in position 1 arbitrarily. Then person in position 2 can have any of 364 different birthdays, i.e. any birthday except the one in position 1. Then position 3 can have 363 because it's any of the birthdays except the one in position 1 and position 2. And this goes on until the nth person. So this is where we get this. But there we assumed that the person with our birthday was in position 1. But it could be in any of the n positions. And we know we've not double counted because we know there's only one person with our birthday. So we just times that by n. And we have the total number of suitable combinations of people we could have in the first n positions to give us free admission. So we have our probability here. So how do we proceed from here? Because doing calculus on this to find the maximum as n changes doesn't feel like a particularly good thing to do. It doesn't feel very easy. So the key is, when this process starts, if we were the first person in the queue, there's 0 chance of getting. And if we were the 367th person in the queue, there's no chance we get in because there would certainly be a pair before us. So we know we start at 0 and end at 0 probability. And we go up in steps of 1. So what we're going to look at is this, Pn plus 1 over Pn. So this gives us the change in ratio of probabilities as we go up by 1. And if we can see when this is less than 1 and greater than 1, we can probably work out the position of n to maximise our probability of getting free admission. So Pn plus 1 over Pn is this over the same with n in, so we get n over n minus 1. All the numbers cancel here except this one, 365 minus n minus 1, and this over 365 is because we get 365 to the n and 365 to the n minus 1 for Pn. So simplifying it all, we get this. So where do we progress from here? Well, let's look at when Pn plus 1 over Pn is greater than or equal to 1. So essentially, if we're in position n in the queue, and this is true, it means we should move back 1 to have a better chance of admission. So this is equivalent to this being greater than or equal to 1. And we can simplify this a bit. So that's times by the denominator on both sides to get 365n minus n times n minus 1 is greater than or equal to 365 times n minus 1. And this is a quadratic inequality. So if we move the n squared over to here, so n squared minus n minus 365 is less than or equal to 0 because we moved the n squared over here. So let's solve our quadratic inequality. So we need to look at the associated quadratic equation. So lambda squared minus lambda minus 365 is 0. So we see this isn't going to factorise, there's very little chance it will. So let's solve it by the quadratic formula. So we know lambda is 1 plus minus the square root of 1 plus 4ac, but c is minus 365, so 1 plus 4 times 365 all rooted over 2. So let's try and sketch what y equals x squared minus x minus 365 would look like, or the quadratic graph. Because we see that lambda, our negative root here, would be certainly a negative number, because we're doing 1 minus something that's far bigger than 1 here. So we know our graph looks something like this with our positive root, which we'll just call lambda for simplicity here, and a negative root here. So we only really care about this position of this positive root because we know n's must be a positive integer. We know it's less than 0 when we're near 0 around here. So we only care about when we cross the x-axis on the way up. So we need to approximate lambda. Now, there's no way to accurately get what lambda is without a calculator, but that's not a worry really, because we're only looking at n integers. So as long as we know the two integers that lambda lies between, it'll be sufficient to work out what n we're looking at here. So what is this? Well, we can see that lambda is slightly greater than root 365 plus a half, because root 4 times 365, well, the root 4 is like divided by 2 here, and the 1 makes very little difference. So this bit's roughly root 365, and they've got the adding a half. Does this help us? Well, yeah, because 20 squared is 400 and 19 squared is 361. So this is very, very slightly bigger than 19. So this is only marginally larger than 19, and we add a half. It means we're going to be between 19 and 20. So we're not sure exactly what lambda is, but we know it lies somewhere between 19 and 20, and that'll do us. We also know it's not equal to 19 or 20, explicitly, because otherwise we would have had some factorisation here. So in fact we have lambda is between 19 and 20 exclusively. So this means that n equals 19 will be less, but n equals 20 will be greater. And so we've completely solved this for n positive. We know this is equivalent to n being less than or equal to 19. So how does this relate to our original problem? Well, we know that Pn plus 1 over Pn greater than or equal to 1 is now if and only if n is less than or equal to 19. So imagine we're in the queue, we're in positions 1, 2 or 3, etc. We know, because Pn plus 1 over Pn greater than or equal to 1 means Pn plus 1 is greater than Pn, that if we're in a queue position 19 or less, we should step back 1 in the queue to have a greater possibility of free admission. But then, once we get past position 19, so we're in position 20, we know we have a worse chance if we step back again. So doing that, we see that the last step we should make is 19 to 20, when n is 19. So the probability that you get free admission in position 20 is better than probability in 19, but then we should stop. So if 19 to 20 is the last step we should make, and any further steps back, no matter how far we go, make our probability worse, we know our optimum queue position is the 20th position, and that is our answer.